we can start.
Hello everyone. So the title of the paper I'm presenting.
Do you want to move here or like here somewhere, just closer to microphones and everything? Thanks for checking, Girish. We had for those on YouTube watching, we had a fire alarm, but it was a false alarm, so we're starting. I'll show your face there. That's a camera.
Hello everyone. So the title of the paper I'm presenting today is learning to exploit temporal structure for biomedical vision language processing. So this paper is about vision language processing, and it tries to capture temporal structure from multiple images during pre-training phase in a self-supervised way. So this paper was presented at conference on computer vision and pattern recognition 2023. The authors are Banur Shulti et al. Right. So self-supervised learning in vision language processing, it basically exploits semantic alignment between imaging and text modalities. So what we got here is we got image text pairs, and then we use the information from image and text to extract features that could be helpful in any downstream classification task. Self-supervised VLP can significantly reduce the need for manual labels, which is required for training. So because it's a self-supervised, we don't need labels. And if we talk about prior work, it mostly relies on alignment of single image and report pairs, which leads to, of course, poor alignment between modalities, because if we talk about clinical notes, they are not just based on single image, but also based on previous prior images as well. So that leads to poor alignment between modalities, and also it misses out temporal content. So the proposed method, they named it Biomedical. It's basically a CNN transformer based method, and it is a multi-image encoder, which means that it accepts prior images as well as along with current image for the pre-training purposes. And then they test the proposed model on various downstream tasks like progression classification, how a disease progresses, different stages of a disease progression. And then they also tested the model on phrase grounding, which is essentially identifying problematic regions within image that a phrase is referring to, like, for example, bounding boxes and stuff like that. And then report generation, which essentially describes what's going on in an image. So these are the tasks that they conducted experiments on. And then they also released a multi-model benchmark dataset, MSCXRT, and they used it for the downstream tasks. Self-supervision from image text pairs has enabled the development of flexible general purpose real models. But if we talk about specialized domains like radiology, like biomedicine, this poses a challenge, which is basically, we know that reports are related to prior images as well, right? As I talked about it earlier. For example, we have this clinical note, pneumonia is improving, and it is, of course, based on prior images, right? It's not just the current image. So this leads to ambiguity during contrastive pre-training. And if we study existing works, they sometimes just remove temporal information, or they just ignore temporal information from reports to prevent hallucination, to remove noise, because those models could not handle temporal information in the downstream report generation task. But the problem is, if we just discard the temporal information from MLBBQ, it limits that MS text alignment which we are looking for during pre-training tests. If you look at the figure, A represents the existing methods and C represents the proposed method. The existing methods, they take current MH, pass it through MH encoder, and then the clinical report, they pass it through a text encoder and get a affinity matrix. In proposed method, they can use prior MH if it's available. Otherwise, this method could work even without prior MH. So they use prior MH, they use current MH, pass it through MH encoder, and then clinical nodes and get an affinity matrix. If you look at B and D, you see info and you see affinity matrix for both approaches. If we talk about spatial modeling, which is B, pleural effusion is worsening, right? So if you talk about spatial modeling, it's not able to get that alignment. But if you talk about spatio-temporal modeling, it is able to get that MH text alignment.
Right. So they only change to the common pipeline they think is added the previous image.
Yeah, so previously they have a baseline which is called Biomedical, right? It just uses existing image, one image. So they have just modified that architecture.
And they adding two images, or they adding some encoding that this is the first image, this is the second, or just entering two images as channels to encode them.
So they just use one prior image for now, but they're saying that their model is capable of accepting multiple images as well.
But it's the same image encoder, so are they entering as like just adding channels to the CNN with the prior images?
So I'm going to talk about this detailed model in the coming slide. Maybe there you get your answer. So the contributions of this paper is they introduce a novel pre-training framework, Biomedical, and then rather than ignoring or removing temporal information, they have developed a mechanism to account for it during pre-training tests. And then they make prior images available for comparison to a given report. And then multi-model image encoder. This multi-model image encoder handles multiple images, and then it also handles absence of prior images. They have achieved state-of-the-art research on temporal-based downstream tasks, and then they also released a new data set that is curated by radiologists, and it's available for everyone to use. And then they achieve good results on non-temporal tasks as well, like pneumonia detection, phase grounding. It's a static task, but getting temporal information helps in static downstream tasks as well. Okay, so the proposed approach comprises of multi-image encoder and a text encoder. So MS text pair. Multi-image encoder basically extracts spatio-temporal features from a sequence of images, and then the text encoder incorporates optional cross attention on image features, which means that if prior image is available, it's gonna apply cross attention. Otherwise, it's not gonna do that. And then the training is done with MS guided masked language modeling and cross model global and local contrastive objectives. So we have a pair of current image and current report, right? And the report describes current image based on information from prior images as well. So if we talk about data sets DM, it comprises of current image prior image and current report. And if you talk about data set DS, if we don't have prior image, then we are left with current image and current report. So the resulting data set is essentially a union of DM and DS. So the encoder is basically a hybrid model. It has CNN and transformer-based architectures. In these two equations, the parameters W, H, and T correspond to spatio-temporal dimensions, and D, MH is the embedding dimension. So EMH is basically encoding we get using CNN-based model. Using CNN, for example, they have used ResNet 50 to get embeddings out of MH, and then AMH is they have used transformer to apply cross attention. And EMH this serves as a STEM network to provide visual feedback, visual token features of individual images. And AMH is embeds captures page embedding inflection across time when this prior image is available. This is the detailed schema. You can see here they have a prior image at the top left. They pass it through a CNN encoder and get affinity matrix. And similarly, they take current image and do the same. And then they use both matrices and do spatial encoding and temporal encoding, and then they get a patent and concatenated representation of both the images. And then they use transformer to apply cross attention on the image and get features. If prior image is available, then we get P diff, otherwise we get P miss. And then similar task is done on text. We mask the vertical nodes and get MLM loss, and then for contrastive loss, we classify here based on the progression of diseases or different stages of it. And then this is pretty much it. For pre-training, they have used this data set, mimic CXR-V2. It contains longitudinal imaging data with corresponding reports. They have used 174,000 text image pairs for training purposes and 4.9K for validation purposes. One thing that they have just used frontal view scans. They have discarded other scans from the data set. And majority of pairs include a prior image. So they can capture temporal information from there. And then no manual labels are used during pre-training if we talk about this proposed method. And for the downstream task, they have used various data sets like MSCXR for phase grounding task and RSNA pneumonia data set to test zero shot and few shot learning. And then the last one is the same data set that they released, and they've used it for temporal sentence similarity and image classification tasks. So for temporal image classification, they have used macro accuracy because the data set is kind of imbalanced. So I think macro accuracy is a good idea to take care of that. And then for phase grounding, they have used two measures, mean intersection over union and contrast to noise ratio. So this CNR measures discrepancies between the science similarities in bounding box regions. And then the last task was report generation. For it, they have used these two matrices, do and rho L. These are the experimental results. If we talk about report generation task, they have basically grouped it into two broader categories. The first one, NN, which is nearest neighbor based, and the second one is auto regressive based, where they have a fine tune using auto regressive. If you have a look at the third column, you see PI, PR, right? PI means prior MH, they have used prior MH, and PR means they have used prior reports. So using PI, PR helps improve model's performance on downstream tasks. You can see if you have a look at the last row, the results are highlighted where they have used prior MH and prior report as well, and then they have used their proposed pre-training, which is bioavailability, and they get significantly higher results if you compare it with other baselines, like baseline NN, baseline auto-regressive, which is like BioVil. So BioVil is a static pre-training method, and BioVil-T is it uses temporal information. And then if you have Jexpert scores, you will know that for the proposed method it's 31, and it kind of measures the factuality of the reports. And for the temporal MS classification, they have categorized it into two parts, Z and F. Z and F is basically zero shot and few shot learning. And then the next part is the fully supervised learning, where they have used they have used labeled data for pre-training. So if you have a look at the first row, you see 0%, right? So they have used 0% of labels, which is zero shot, and the pre-training method is temporal. And if you compare it with CNN plus transformer, which is a supervised approach, the BioVil-T outperforms the supervised method. And then if you just use 10% of labels, which is the second row, BioVil-T 10% of labels, it jumps from 53 to 59, I think, which is a significant achievement. And then non-temporal baseline, which is BioVil, is non-temporal. And if you compare it with BioVil-T, which is the last row, you can see it jumped from 56 to 61 if you talk about consolidation, and similar results you can witness in pneumonia, edema, and other diseases. So baseline methods, they rely on MS registration underperform. This is the third last row, BioVil with regression, with registration. So with MS registration techniques, still BioVil-T outperforms the other methods. So this is a results of MS classification on pneumonia detection. So pneumonia for this classification, we could only use single MS, right? Single MS, and we can detect pneumonia. And this is a static task. And they have mentioned percentage of labels. When they just use 1% of labels, the accuracy is 81%. So they conclude from this table that even static tasks benefit from temporal information, which is acquired during pre-training phase.
Can you explain? Can you give an example of a static task and how it benefits?
So this is the task, right? They have to predict whether they have to predict look at an image and predict whether a patient has pneumonia or not, right? So this is just based on the current image, not like a series of images. So in that sense, they say this is a static task.
But they are predicting on series of it. They're adding information, right?
Yeah, they are adding information, and they're saying if you add temporal information, it's helpful. It gets good results. Okay, and then the last task was phrase grounding. Phrase grounding. So this task also is a static task because you can solve it with single image. However, inclusion of prior images doesn't impair the performance of viability. So here they're saying that if we include temporal information, it's not going to impair the results, right? If you take a look at the last two rows, it's 1.33 and 1.32. So they are mostly same, right? So if you even if you use multi-image, it's not gonna distort your results or something like that. So it's gonna preserve localized information from the current image. I think the take-home points are that temporal pre-training yields data efficiency. You can work with less data and still get state-of-the-art results using this self-supervised pre-training method. And then then a wide range of downstream tasks benefit substantially from temporally aware pre-training, including static tasks as well. So static tasks also benefit from temporal learning. And then temporal information helps in producing high quality sentence embedding. So they did experiments on sentence embedding as well. They had a table, I didn't include it here, but yeah, that showed it. So I think this is an excellent work. They have done a lot of studies, but I think in future maybe diverse data sets could be used and see if this pre-training method works. Maybe we could use a fMRI, do this on fMRI if we have a data set available that has some textual information, and we can try that and see if it works in a similar patient. That's it from my side. If you guys have any comments or questions, please feel free to ask.
Yeah, thanks. So any questions online or here? Any use the paper?
I was just curious. I'm mainly curious how it relates to this kind of research, but paper.
Well, it's self-supervised, so that's self-supervised training.
Yeah, the part that was interesting to me was, I mean, the fact that they were taking like doctors' reports and using that as supervision.
But it isn't. No, it isn't. They're using contrastive learning. There is no supervision. It's just multimodal contrastive learning. It's all back to Dev and Alex paper that people provide. They can patch it. But it's interesting that they didn't simply add the temporal information or like a prior image, but they use the embedding for those, and then they use the attention to be kind of like sequential. You know, there is a sequence of this feature. The first half of the features come from the previous image, and the second half of the features, and they use transformer to do the third. I don't know, it's not a visual transformer, it's just a vector, regular transformer, right? Because those are embeddings already in the vector space, either in patches or anything. Why are they using patches? Do you know? Like you embedded the image already, the entire image. So you can use it as your sequence or what are the patches there? Like what are they packing? I
don't know, but the transformer, they used it to apply cross attention on those features that they got from CNN decoder. So
yeah,
that much I know. But
yeah, but what are those features? They call them patches, but you are applying it to the embedding, to the features. You take two images, you apply the same encoder, you get the embedding. Now you somehow order those embeddings and in the sequence, and then you apply your transform. So the patches is that ordering, but how do they patch? I don't know, maybe Alex knows. How do they patch the embeddings with respect to the original image, like the field of view, or how? It's interesting.
go back to the slide, this model architecture?
The on page, yes.
Here. Another thing it's interesting to me that when you have, at least judging by this picture, and just the logic, the embeddings, the B there on the far right, the embeddings are quite large, right? You've embedded everything. It's not like when you in a transformer or any other sequential textual, you have a missing token. Missing token, you have thousands of tokens, and this is just one missing token. But here, this top missing token is added everywhere. So I'm surprised that it doesn't overwhelm the learning. But when like, either it doesn't matter, like the number of data points in their data set with missing token is very small. Or but imagine half of them have the same missing token. How does the model learn to actually treat it as an interpreter as helpful? That's interesting. And they do not compare with any supervised training, right? They only compare with that previous model.
Yeah, Biomedical, yeah. No, so Biomedical is like, just take into account one image, not prior image.
Okay, but it's maybe we don't need the supervised methods at all. Maybe supervised perform much better. Yeah. Even with smaller data that is matched. How do we know? It's kind of like a nice toy exercise, but you don't compare with supervised.
They have done comparison with supervised methods. They used Biomedical, but they used supervised learning, like used all the labels and then they get good results. Like to have a look at last two.
So they trained all the models in supervised fashion as well.
Yeah.
But then, okay, so supervised for T gives us 68 on edema, 67. How does this compare with unsupervised on the same task?
Unsupervised.
Yeah. Do you have this table for unsupervised?
No, they don't have that.
Yeah, I just wonder if supervised, unsupervised, or self-supervised is needed at all.
Yeah. So the first part is self-supervised, right? So first they have used 0% labels, which is 0 short learning, and then 10% of labels to short learning.
So supervised is better.
Yeah, supervised is better.
So what is the motivation for this work then? I thought the motivation for this work is to improve over supervised by employing events.
I think they're using temporal information. That's the thing.
No, with step back, why are they doing the work at all?
Well, I think from what I hear, and this, of course, a lot of the methods, but at least from this part, it seems like they are just comparing, like, few labels are available versus no labels, right? So 10% of the full label set and then none of the labels at all. And of course, it's better if you have some labels, but you still don't want to leverage. But I see what you mean, where it would be better if they compared, if you had all the labels. Right, but yeah, I think that's not like the use case here. The use case is you have a bigger data set but only some of the data sets are labeled, right? So what you want to do, I guess, is knock out.
But you need to compare
Yeah.
supervised training on this subset of.
Yes,
vehicles.
that's what,
With
yeah.
self-supervised, maybe we fine tune. That's how we usually do.
Did they-
Otherwise, it's.
Did they do the model on just that 10% of labels? I can't imagine it would be great because it's a smaller data set, right? So, but that would be a good thing to ask for. Let's see.
And well, I kind of have an allergy when people compare only to a previous model, which was already compared with everything, because that already compared and published. They got lucky, because the reviewers didn't compare with the right baselines. And now everyone is only comparing to this model as the best, but
Yeah, I think that's good.
it's not, yeah, so I'm not too sure. And then the supervised comparison is also important, because the point, I think, is to replace supervised when the labels are not around. But if supervised still fits you in the regime of law data, so you want a foundational model of some sort, you want some pretraining that you use for some task afterwards. So that has to be demonstrated that not going for the task straight directly.
Yeah.
Is not better, or like a tipping point, like the space transition diagrams, when the supervised fail out the amount of label data, and when it fails, when it starts working, that would be informative at least. It's kind of, I find like they've done a lot of number crunching, but I find it not helpful to me. Like, that does not answer my questions in terms of is this model. But the approaches are very useful out there. Okay, if there are no any other comments, I think we're done with this paper. Maybe people want to talk about.
Does that have code available for it? 'Cause then,
Yeah.
You know, we could try this.
Talk about it.
Yeah, why not? So if you see a shortcoming in their evaluation, let's try it, run it and see how prepared.
Do you have, before I stop recording, do you have a MRI data with, Dr. notes or MRI data with Dr. notes for brains and one?
I think Vince has talked about there being a data set like that. I don't know if we actually have our hands on it yet, or if it's just a collaborator has it, and it was maybe a use case for one stack or something. I don't have the.
Yeah.
Jeremy might know as well.
Yeah, that would be. Okay, thanks everyone for watching. Bye bye.